Good morning, everyone, once again, and welcome to another session of the JKMRC Friday Seminar Series. So, on behalf of the University of Queensland and the Sustainable Minerals Institute, would first like to acknowledge the traditional owners of the land, the Turrbal and Jagera people, and pay our respects to their ancestors and descendants who continue cultural and spiritual connections to country. It's my great pleasure today to welcome Dr. Chris Anderson. Chris is a process engineer with over 15 years of experience in the design and commissioning of mineral processing plants. He's a registered professional engineer with the Engineering Council of South Africa and holds a PhD in the area of flotation. He's fulfilled various roles within the engineering procurement and construction management environment, including lead process engineer, study manager, commissioning manager, and has been involved in full life cycle projects from concept to commissioning across a range of commodities. He's currently working as a Senior Metallurgist for Glencore Technology, where he focuses on the development of the Jameson Concentrator for applications to base metal and PGM projects. Please join me in welcoming Chris.
Thanks very much, Daniel, and thanks for the opportunity to make this presentation today. The title of my talk is Doing More with Less, the Jameson Concentrator Approach to Circuit Design. This is a new concept in terms of going about circuit design for flotation circuits, which is unlocked by the technology that Glencore Technology markets, the Jameson Cell. So what we'll be going through today, starting off with some market drivers. Why do we need to do more with less? Why do we have to be more efficient with our design approach? I'll then go through some of the traditional methods of conventional circuit design and give an overview of the Jameson Cell and how it's different from conventional cells. I'll go through a few case studies in rougher scavenger applications and show how this is unlocking some of the potential for full concentrator circuits. I'll then go through our methodology with Jameson concentrator circuit design, as well as some case studies where we've applied this. And then I'll finish off with some recent developments and further research. So let's start by looking at some market drivers. Why do we need to do more with less? Well, first of all, we are all aware of the commitments that have been made to a net zero future. As part of this drive, the world needs to transition away from fossil fuels and over to renewable resources. However, as these renewable resources require a significant amount of metal to produce their power, there's going to be a significant demand on the mining industry to deliver those metals. The graph on the left shows the amount of metal required per megawatt of power. And as you can see, solar power and wind require substantially more raw materials compared with coal and natural gas alternatives. These clean energy technologies are driving a 40% increase in copper demand over the next 2 decades. And this is led by an increased demand for electric vehicles, as well as wind and solar power. However, the current supply of metals is not rising to meet this demand. Over the last 10 years, relatively little copper resources have been added to the global resource base, mostly due to a lack of exploration. Added to this, the projects which are coming online are relatively low grade and not adding significantly in terms of the total megatons of copper produced. Projects are also becoming more expensive per ton of copper produced, and it's becoming increasingly difficult to obtain approvals for new projects. This is shown by the graph on the left, where you can see that the average copper project takes approximately 12 years between discovery of the resource to the ramp up to full production. And what this means is that there is a looming supply deficit emerging. What is required is that we reduce the cost of doing these projects and that more projects can make it through feasibility and into execution. And we need to design these projects in a more sustainable and responsible manner so that they can receive the required permitting and can start to deliver the metals we need to transition. So with that context, let's examine the traditional approach to concentrator design. So traditionally, flotation circuit design begins with a 2-liter Denver cell. We put the material in the cell, we optimize the grind size and the reagents, and we produce a series of kinetic curves, which are aimed at determining the residence time for each of the banks. This curve is fitted with a well-known first-order rate equation, where the recovery is given as a function of the residence time and of the rate constant. Upon knowing the required residence time in the batch cell, the result is scaled up by an empirical scale-up factor of 2.5. So, for example, if you found that you reached your target recovery in a batch cell in 10 minutes in a laboratory cell, you would design the full-scale flotation bank for 25 minutes. Now, admittedly, I am oversimplifying this somewhat. There are improved models that have been derived to model and scale flotation, most notably Kelsor's equation, which uses fast and slow floating components, as well as Garain's equation, which incorporates some parameters for air rate as well as entrainment. However, the dominant thinking tends to be that instead of improving the rate constant in this equation, we can simply increase the residence time. And for most of flotation history, that is the approach that seems to have been followed. So from an engineering point of view, it's often easier to build things larger rather than to make them more efficient. As you can see, the size of the flotation cell has increased exponentially. Cell sizes have increased from 2 cubes in 1940 up to now 630 cubes in 2018. By extrapolation, if this trend were to continue, we would expect flotation cells above 1,000 cubes by 2030. However, increasingly, the industry is starting to question the limits to this approach. For example, Finch recently published a technical note on the possible limits to cell size. The reasoning is that while the volume increases with the diameter cubed, the cross-sectional area only increases with the diameter squared. This means that the larger the cell, the more surface area per ton of concentrate produced, and therefore the lower the carrying capacity. This additional area could therefore lead to froth stability and carrying capacity constraints. This is particularly relevant for scavenger applications where the mass pull in an individual cell is very low and froth stability is compromised. Then, of course, there's the maintenance requirements. Maintaining large mechanical cells requires periodic removal of the agitator mechanism, resulting in an inherent safety risk with working under large suspended loads. Secondly, in a large concentrator, there can be a significant number of cells to maintain, with competition for crane access resulting in longer downtimes. So what alternatives are available into the Jameson cell? So the Jameson cell is a relatively old technology. They've been in operation for over 37 years, and we are rapidly approaching 500 cells installed worldwide. Over this period, the technology has been gradually refined and perfected, with continuous improvements made based on feedback from real-world operations. The technology is currently in its 5th generation, incorporating the learnings of each successive installation, resulting in a robust and simple cell to operate and maintain. The cells are highly effective, from very fine particles of down to 2 microns, right up to 400 microns in base metal applications. The units are fast and self-stabilizing and are able to react to a wide range of feed variability. The system incorporates a tails recycle mechanism, which ensures a constant feed to the downcomer and therefore a consistent hydrodynamic environment for flotation to take place. They have a large carrying capacity owing to their small bubble size, reducing the footprint required for high mass pull applications. And the cells are self-aspirating, meaning that no blowers are required. They can also be operated very flexibly, either as a high-grade unit with very deep froths and high wash water, or they can be operated more aggressively with shallow froths and very high air to pulp ratios, resulting in high recoveries. So how does the Jameson cell work? Well, at the heart of it is the downcomer, which is shown on the right-hand side. And essentially what we have a slurry lens or an orifice where the slurry is injected into the downcomer and plunges down into a bed of essentially entrained air and highly turbulent slurry. Now, in contrast to a conventional cell, 100% of the feed must go through this downcomer. So each particle in the feed will go through this highly turbulent zone, and the probability of collection is almost 100%. If one considers the alternative, a stirred tank cell, it's really a probability game. Cells are designed on a number of passes through the impeller, with the hope that each successive pass will result in a successful collection. So because of that, the Jameson cell does not depend on residence time. Each cell will go through that contacting zone, and the probability of collection is approximately 100%. So if we were to plot it on a kinetic curve, the Jameson cell would sit at a very low residence time with an equivalent recovery to a bank of flotation cells. The second part of the Jameson cell's advantage is froth washing. So it incorporates a very simple but effective froth washing ability, where we apply a net positive flow of wash water that effectively washes all entrainment out of the concentrate. This allows the cell to produce a very high grade, but as that wash water is pulled back, the cell can also achieve a very high recovery. This is a schematic of a Jameson cell. So the feed box is given on the left-hand side of the cell. Material is pumped out of that feed box and into a distributor, where it's distributed through multiple downcomers. Material is then discharged into the tank part of the cell, and the concentrate goes over the launder. The tailings comes back down through the bottom of the cell and passes either back into the feed box to be recycled, or through the start valve and out to the next part of the circuit. The Jameson cell's key advantage is that it's able to produce a very fine bubble size. So typical bubble sizes in the Jameson cell are approximately 0.5 millimeter, significantly lower than most mechanical cells. And this allows us to collect in a very wide particle range. So this is a survey that was done by the JK at Mount Isa in 2017. And as you can see, the recoveries between 3 microns all the way up to 300 microns is well into the 90s for the Jameson cell. So this would be equivalent to conventional cells. However, conventional cells would be limited with their fines collection ability. So yeah, a very wide range of particle sizes able to be collected. So let's have a look at a few case studies. While most people are aware of the Jameson cell's high performance in cleaning duties, many people are not aware of the Jameson cell's performance in coarser, rougher, and scavenger duties. Presented here are the actual results from a Jameson cell in rougher duty, meaning a single Jameson cell. In many of these cases, the cell was operated with a focus on grade rather than recovery. Now, it's important to understand the significance of performance of a single cell, and then you can understand why the Jameson Concentrator, which I'll discuss shortly, is so small. The trend that we see in rougher applications is fairly consistent across multiple sites. Initially, the cell produces a very high grade concentrate, corresponding to the grade of the most liberated, fast floating material. As the cell is adjusted to pull more and more mass, we start to pull more and more middlings material, and the grade of the concentrate starts to go down. In general, the rougher is able to produce between 70 and 90% recovery at final concentrate grade, leaving relatively little work for the rest of the circuit. Here are a few more rougher results. So on the top graph, we have both dilution cleaning results, and we have results from the pilot scale Jameson flotation cell. And once again, the curves follow the same trend. So it starts out with a very flat portion corresponding to the grade of the liberated material. And as we start to collect more and more middlings material, the grade recovery curve starts to turn down. We see similar results across a number of sites. So in this case here, also achieving a very high grade, about 45% copper, at a recovery over 80%. In this example here, once again, achieving around 80% recovery, again at saleable grade. And we see a similar trend for other commodities. So at the bottom is some lead and zinc examples. But once again, if the material is liberated, it typically can be taken out of the circuit at final concentrate grade in a single cell. This is an example from our largest installation, the Z8500. So once again, we've got the dilution cleaning test, which established the grade recovery curve. There was pilot work done to prove that performance could be achieved again. And we find from the latest operating data that indeed the cell's performance does sit on that grade recovery curve. What was also interesting is that the cell was relatively insensitive to percent solids. So although the plant was getting a wide range of percent solids presented to the cell, right down from 25% up to 50%, the performance of the cell was relatively unaffected. This is an example from the CIS region where the Jameson cell was operated in two modes. So first of all, as a rougher scalper, where we were able to produce a 28% copper grade at 89% recovery. We then took the same cell and slowed it down a bit. We operated at a lower grade, 22% grade, collected the tails and then ran it back through the cell. And in this example with two stages, rougher and scavenger, we achieved 94% recovery using only two cells. This is a similar example from an IOCG deposit here in Australia. And once again, the Jameson cell was able to perform extremely well relative to the conventional cells. Overall, we achieved a 95% copper recovery across the rougher and the scavenger, compared with a 93% recovery across the existing bank of 6 cells. This was also done at a higher grade than what was achieved in the conventional cells. And we were able to scalp final concentrate from the rougher. So what would that look like in practice? This is an example of a B8500 cell operating as a rougher and a B8500 operating as a scavenger. And as you can see, two Jameson cells operating in series can occupy a very small footprint. So in this case, this plant can do 14 million tons per annum, and it can fit into a 30 by 20 meter footprint. So how does this affect our approach to circuit design? Well, firstly, let's take a look at the traditional approach. If we take our results from the 2-liter batch cell and we apply the 2.5 scale-up factor to get to the full scale circuit, in this case, a rougher scavenger with long residence time to drive recovery. The rougher concentrate is fed to a regrind mill with 3 stages of cleaning in closed circuits in an effort to drive concentrate grade. The result of this approach is a circuit with long residence times and high recirculating loads. In addition, the full rougher concentrate is directed to the regrind mill, resulting in liberated particles which were ready for final concentrate, becoming overground and ever more difficult to recover in the cleaners. Circuits have been designed like this for decades. However, this design approach is rapidly becoming outdated and unnecessary. So let's have a look at some alternatives. In a Jameson cell, we have a different approach, an approach which does not rely on any scale-up factors. What you get in the test work is what you get at full scale. And we do this by establishing the grade recovery curve of a given material. We have several means of doing this. First, we can apply a dilution cleaning test, where we float the material multiple times to simulate the effect of removing entrainment. Essentially, what we're doing is separating the material according to its floatability, with the most liberated material removed first, followed by the less liberated material, followed by the middlings material, and so on. Incidentally, this test was originally developed for coal for ash yield curves, similar to the float sink analysis they do for DMS. Thus, the output of the test should be seen as a function of the ore's mineralogy and liberation characteristics rather than of a particular operating condition. Or as an alternative, we can use the pilot scale L150 Jameson cell, which can be run in a laboratory environment with approximately 20 kgs of sample, and it can produce the same grade recovery curve. We would expect a marginal improvement using this device due to the improved fines collection of the Jameson cell. However, essentially the two tests are generating the same grade recovery curve, which is used for design. And finally, the gold standard in test work is the demonstration plant, the Z500, which is a pilot unit which can be sent to site to operate on a live stream from the plant and establish the grade recovery curve. So this test work information is then used to compile the grade recovery curve, which is at the heart of the circuit design. So typically the curve starts with a flat horizontal portion corresponding to the grade of the fast floating liberated material in the feed. Often a significant portion of the valuable mineral, usually 70 to 80%, can be recovered above the target final concentrate grade. From a design perspective, the material is recovered in a rougher scalper unit, which is set up with a deep froth, a high wash water, and a low air to pulp ratio. The remainder of the recoverable material, consists of unliberated middlings particles, which require further regrinding before reporting to final concentrate. This material is recovered in a scavenger unit, which operates at a shallow froth depth, low wash water, and high air to pulp ratio to maximize recovery. And it's worth reiterating that there are no scale-up factors applied with this approach. What is achieved in the test work is what we achieve in the final design. So looking at it from a whole circuit perspective, this shows you the parts of the conventional circuit that the Jameson cells would replace. And every Jameson cell is designed to either target final concentrate grade or to target a high recovery. So each cell in the circuit is given only one job. Liberated material is removed from the circuit as early as possible, preventing overgrinding and potential losses in the downstream cleaner circuit. Recirculating loads are kept to a minimum to allow the circuit to react quickly to changing flotation conditions. The aim being to ensure an efficient circuit which minimizes unnecessary flotation and buildups of slow floating gangue. And this is an example of the type of circuit that we would end up with. This example uses our largest B10500 cell with 16 downcomers and is able to process 15 megatons per annum. As you can see, the larger, rougher scavenger cells are at the back, with the smaller, cleaner cells in the front. The regrind mill located alongside the flotation cells, resulting in a very tight footprint of just 30 by 45 meters. Height is restricted to 17 meters, which is particularly significant, given that you don't need a crane to remove any agitator mechanisms, which would normally add significantly to the building height. This is also particularly relevant for cold weather areas where plants are typically enclosed in buildings. So if we compare the Jameson Concentrator approach to a conventional circuit design approach, the magnitude of the differences become apparent. So application of the Jameson Concentrator approach reduces the number of cells from 19 cells down to just 5, and the installed power from 6.2 megawatts to 2.7 megawatts, which is a 57% reduction. However, this is only a hypothetical case. So let's look at some real world examples. So this is a model from a recent lead zinc concentrator, which processes 875 tons per hour. It's currently under construction. There are 19 Jameson cells, which replace 63 tank cells. It makes use of 3 of our largest M20,000 IsaMills. The footprint reduction is over 50%. There's reduced height, which means reduced heating. There are no air blowers and therefore less noise, less power. It's safer with less height and less confined spaces. And there are significantly fewer spares compared with a conventional circuit. So this is a video of the concentrator currently under construction. It's located in a very cold weather country, so everything is indoors. There you see the IsaMills. And this makes use of our B8500 cells. Okay, so that plant is currently under construction, should be undergoing commissioning very shortly. This is New Britannia's Hud Bay operation. So it consists of a rod mill targeting a P80 of 75 microns. It was designed with a pre-float circuit for talc, and my understanding is that they're not running that pre-float at the moment. It has 3 cells as the rougher and scavenger, and a single cell as the cleaner. It's a flexible design with the ability to reroute concentrates to various parts of the circuit, and that makes use of the Jameson cell's ability to react to different feed flow conditions. So we had 4 Jameson cells, which replaced a circuit of 12 tank cells. No blowers or compressors were required. And this resulted in a 50% decrease in footprint and in power. It was water commissioned within 2 days and achieved the target tails grade within 24 hours of starting. The circuit's been operating at full capacity and achieving design grade and recovery. And this is just a comparison between the pilot grade recovery curve that was developed for the project and some of the recent operating data. So we can see that the plant is actually exceeding the upgrade ratio that was expected and operating at the expected recovery. So Hud Bay has been very happy with this result and has also extended the use of Jameson cells to their stall concentrator, which was commissioned earlier this year. And these are just a few examples. There are quite a few other Jameson concentrators in the pipeline at the moment. So looking at some new developments, some of the work that we're busy with extending our research. This is a few slides showing the effective recycle. Has been a bit of a debate with the Jameson cell. The Jameson cell incorporates the recycle for the purposes of process control rather than for metallurgical reasons. And we've been doing some test work to prove this. So we've been varying the recycle between 0 and 50%. And what we see is that between about 20% and up to 50%, there's very little impact of recycle on the metallurgical performance. Below 20%, down to 10%, and even at 0%, one can see a slight drop-off in the recovery. But overall, there's some consistency in terms of where the performance lies as a function of the recycle rate. We've also been looking at alternative Downcomer designs. One of the reasons for this is to try and see how coarse we can float with the Jameson cell. So in this example, we've got a fluted design where we basically expand the Downcomer towards the bottom here, and then we also put a deflector plate to try and direct the material sideways rather than down vertically. And what we can see is a slight improvement in terms of coarse particle recovery, both for coal and for base metals. However, it could be argued that you do lose some of the fines performance in doing this. This is an area of ongoing research. There's certainly a lot of optimization we can do with this Downcomer, and that's something that we're busy with at the moment. In terms of the IsaMill, one of the focus areas at the moment is trying to grind coarser. So currently IsaMills are designed to grind from F80s of 400 microns and a P100 of about 1 millimeter. But increasingly we're trying to challenge this. And the reason why it's coming up now is essentially because the media producers are producing coarser and coarser media. So previously we were using 6 millimeter as our maximum size. You can now on the market get up to 16 millimeter ceramic beads. So yeah, a lot of our R&D focus at the moment is trying to process streams that are much coarser than what we have before. And then coupled with this is alternative grinding disc designs. So there are various permutations that we've tested. The idea being to increase the specific energy consumption. And with that view, if you can increase the specific energy consumption, you can reduce the speed of the mill and therefore go for coarser grinding applications. So some of our successes, we've had some success with knob disc designs, where we managed to reduce the baseline power draw. So achieve the same baseline power draw with 10 to 15% less media. We're also looking at online analyzers for the IsaMill. So in this example, an acoustic particle size analyzer, which can be mounted on the outside of a pipe and can be used for process control. So to conclude, a quick recap of my main points. The efficiency of the contacting in a Jameson cell has allowed an alternative approach to concentrator design. It's well proven, low risk alternative with decades of learning, and it offers significant reductions in footprint, power, capex, and opex. It reduces circuit volumes and circuit recirculation, making it simpler and more responsive. And it removes liberated particles from the circuit as early as possible and prevents any chance of overgrinding. This has resulted in significant power and footprint savings up to 40%. And it provides a safer and more sustainable solution to meet the industry's future needs. Thanks very much. And if you'd like to know any more, please contact us on either of these addresses. Thank you.
Chris, that was a really interesting presentation. I'm going to open the floor up to any questions.
Hi, Chris, great talk. I was just wondering, we see increasing use of reflex classifier, particularly in coal side of things. So, I was just wondering if there is any comparative study between Jameson Cell and reflex classifier.
Do you mean the reflex classifier gravity separation cell?
Yeah, something like that. And why, maybe it's just a very basic question, that why do we see an increasing use of now reflex classifier in the coal industry?
Yeah. So look, I think that the choice of your type of separation in coal is going to be very dependent on the mineral that you are processing. So, you know, if you see in your float sink analysis a significant amount of low ash material that you can get out with gravity separation, you would apply gravity separation. Whereas if you only see that sort of low ash product being achievable with flotation, then you would apply a flotation cell. But I don't think they're directly comparable. You know, I would rather first separate, are you going to do gravity separation or are you going to do flotation, before you get into what technology specifically you're going to apply. Yeah, you could. I mean, for example, you could take the product from a reflux classifier and put it into a Jameson cell. It really depends on how the mineralogy is guiding you, how you would do that.
All right, I'll just check the online questions.
Yep.
So we have a question from Grant Ballantyne. Is there a similar limit to Jameson cell sizes as there is in mechanical cells?
That's a good question. So at the moment, the largest installed cell we have is the B8500. And essentially the way that we scale up our Jameson cells is by adding more and more downcomers. So in essence, the heart of the Jameson cell is in the downcomer, and nothing changes about the downcomer as you get bigger. There is a step when you go from the 6500 to the 8500, where we went from a 280 mil downcomer to a 500 mil downcomer. And that particular scale up has shown itself to be very good. So we still get performance on the same grade recovery curve. And essentially what we're looking to do now is just add more downcomers to the same design.
Just on the downcomer, so you mentioned an alternative design was putting those deflector plates in there. I imagine those would suffer a lot of wear and tear. Is that the case?
The velocities around that downcomer are actually not as high as you would expect. So there's obviously very high velocity through that slurry jet that's running a ceramic slurry lens, which is designed for a very high wear environment. But as you come out of the downcomer, you know, the velocities are getting down to, you know, at a few meters per second. Yeah, much lower wear conditions than in the top of the downcomer.
All right, we have another online question. So has the Jameson cell been used in the nickel sulfide ores? How's the performance?
Yes, there are a couple of nickel applications. What I would say to that is basically a Jameson cell is providing the hydrodynamic environment for flotation to take place. So essentially, we're expanding across more and more commodities, and wherever flotation would normally take place in a tank cell, it could take place in a Jameson cell.
That feeds into the next question we have online. So from Rob Stevens, what has held back the adoption of Jameson cells in larger concentrators, and why is that changing now? And what do you forecast to be the maximum feed size for IsaMills with 19 mil feed and the associated energy reduction compared to other technologies?
Okay, so the first part of the question is, I suppose, historical. You know, when the Jameson cell was first developed, its major advantage was that froth washing. And people saw that it could provide a very high grade. So immediately when you get a cell that can give you very high grade, your first thought is, well, let's put it in the cleaners and get the highest concentrate grade we can possibly get. And for a long time, that's where the Jameson cell was marketed. So there are multiple examples of cleaner scalpers being retrofitted to existing plants or put into new plants, that then expanded to re-cleaners. And then eventually it went to full cleaner circuits. So a good example of that is the Mount Isa circuit, where we have 3 cells that replace the entire copper cleaner circuit. And then ultimately people started asking, oh, well, why can't we do this as a rougher? And that's really been the focus, I would say, over the last couple of years. So every time when we test it as a rougher, the results are you know, as I've shown, they're very good. So we're starting to see more and more rougher scalpers. And then if you extend that now to the scavenger, you've basically got a full circuit design that's possible. So I suppose it's just some, the industry takes a while to adopt new technologies and a while to adopt them in new applications. So that has taken quite a bit of time. The second part of the question was the IsaMill.
Yep. So what do you forecast to be the maximum feed size for IsaMills with 16 mil feed and associated energy reduction?
Sure. Okay, that's very specific. I'd have to actually come back on specifically what it would be at 16 mil. But in principle, we're certainly trying to target well up to 700-800 micron as a feed. But as I said, it is an area of research. At this stage, our highest installed IsaMill is at 400 microns.
Is there any reason, or are there any downsides to the Jameson cells? Is there any reason why you would build a conventional float plant as opposed to a Jameson cell plant?
Well, I think, that there's a lot of conservatism in the industry, and a lot of people particularly want to put conventional cells in the rougher. They want to put conventional cells as clean as scavengers. But I think it's down to familiarity, and it's the way that it's always been done, and it's seen as a low risk option. But I think what I'm trying to show with this presentation is that if you apply the technology throughout the circuit, you can unlock some major advantages that are not there if you consider a hybrid circuit.
Thank you, Chris. It was a really good presentation. One thing that really strikes me is that with all the development of the Jameson technology, when it comes to doing lab assessment, we're still using demo cells. And from a research perspective, that is remarkably frustrating. Is there any plan to develop a bench scale Jameson that could be used from the word go?
So I think that we're pretty happy with the three-stage dilution performance. The problem with going smaller and smaller in scale with the Jameson cell is it just starts to become, very difficult to sort of set the test up correctly. You've got this the Downcomer height doesn't change with scale, right? So as you go from the L500 down to the L150, the height stays the same. Now, if we were to go to, say, an L50, a very small Jameson cell, you would start to battle with some practical things, wall effects, getting the slurry jet to be exactly vertical, that it doesn't hit the wall. There would start to be some practical constraints with running continuously through that unit. It's not really something that we're looking at. What we are trying to do is redesign that L150 to be more user-friendly. So at the moment, there's a couple of practical issues that the lab struggle with. There's some redesigns that we're busy with that should improve that.
Thank you.
Thanks, Chris. Early in the presentation, you presented that the Downcomer does everything and everything's going to float. But then you started talking about making adjustments, which changes the mass pull. Can you go a bit more on those? And also, you mentioned liberation as a driver for that different recovery. Any information or knowledge on mineral texture, such as coliform mineral particles, whether they need more or less time for that probability of attachment to take place?
Yeah, so I suppose the Jameson cell can be seen in two parts. So you've got the Downcomer, which gives you that sort of very high air to pulp ratio, very high number density of bubbles, and a very highly turbulent environment. So essentially, you're slamming this jet of slurry into a foamy bed where you're going to get significant contact between air and particles. So that should give you almost 100% chance of collision. Where you can lose it is as it comes up to the froth phase. And that's really what's driving the selectivity. So as it comes into the froth, there's a probability of detachment. Within the froth, running a higher froth depth, you would start to run lower froth recoveries. And essentially, that's where you are choosing which particles you're going to take and which ones you aren't. Then with regards to liberation and textures, I don't know that we have a lot of data looking at texture as an actual variable. But I would say that it's basically an artifact of floatability, and whatever that would constitute, whether it's liberation or size or texture or collector coverage, you're basically choosing the most floatable material first, and then gradually adding less and less floatable material as you go on.
Using the froth depth as your control.
Yes, the froth depth and the froth washing, and the air rate as well.
Yeah, hi Chris, thanks for the talk. I guess a question about you've spoken about traditional conventional cell versus Jameson. What else is out there that's potentially a competitor or a new technology that could disrupt where you're going? Is there something else or some other technologies being developed?
Yeah, okay. Look, I don't like to talk about competitors' products, but I mean, we're all aware that there are competitors out there. I think the advantage that the Jameson Soul has is just that it's a very mature technology. It's come a long way in its engineering life cycle. So a lot of the kind of nuts and bolts issues that some of our competitors may experience, we've been through those learnings already, and it's become a much more mature and robust technology. But that said, I mean, we can't afford to sit still. Obviously there's a lot of focus around this. This is not just us thinking around different types of concentrators. So I think we've got an advantage at the moment, but yeah, we need to stay on our toes and keep developing and stay ahead of the curve.
All right, we have another question from online. So Roger Jackman asks, have you looked at combining your circuits with pre-concentration or coarse gangue rejection to further reduce the size of the circuit and decrease energy usage?
Yep. So there are quite a few projects within Glencore that are looking at coarse particle flotation. So specifically, I think of El Pachon as a greenfield Jameson concentrator that's been proposed. That does incorporate hydrofloat up front for coarse particle flotation. So yeah, certainly it's a type of design approach that could be combined with pre-concentration quite easily. With either technology, I know that there's hydrofloat. There's also a couple of competitor products.
Hi, Carolina here. Thanks for your talk. It was very interesting. I just wanted to ask, which is the operational strategy to apply when you have, for example, only one Jameson in the rougher circuit, and then you have half of the throughput in the plant. But let's say, for example, if you have a maintenance, and then you have to run your circuit with only half of the throughput.
Okay. Yeah, so for a Jameson cell, it's quite simple. If you simply reduce the feed by half, the recycle will automatically adjust. So it maintains a constant flow through the downcomer, and it will just recycle more tails to compensate for the lack of feed. So there's not actually something that the operator needs to do as such. I suppose in low mass pull applications, you need to be careful because now you're going to be producing less concentrate and you would lose a bit of froth stability. So issues like that can start to factor in. But for the most part, the cell is self-stabilizing. So if you change the feed rate, the cell simply adjusts.
Ray Koenig, and thanks for the talk, Chris. In normal flotation cells, you can get short circuiting of your valuable particles, even after 5 stages of roughers, for example. Do you get any at all there, therefore, in a Jameson cell?
Yeah, so I mean, our thinking is that, well, certainly from the test work that we've done, it doesn't appear to be a significant amount of short circuiting. In just 2 cells, you are achieving the same recoveries as what you would get down a bank of 6 cells from a conventional circuit. So it does appear that the short circuiting issue that you get in a mechanical cell is far less significant with Jameson cells.
Well, that's handy because there's always a discussion when we're designing flotation banks, how many cells do you put in? And I guess it makes it easier if there's less short circuiting.
Another question from online. So is there any ongoing technology development on conditioning that may provide an additional advantage to flotation?
Yeah, that's a good point. So obviously the Jameson Soul relies on the material having contacted the collector up front. So it is an area where you do need to make sure that your design is adequate. It's not specifically an area that Glencore Technology is involved in, but certainly something that if we're designing a Jameson concentrator, we'd want to look quite carefully at the amount of conditioning time that the material needs, and just make sure that there is enough room in the design to give you some flexibility there.
Thanks, Chris. Very good talk. Impressed with your much reduced power consumption and so on. A little bit of a left field. When you do lots of field work and you've obviously got a huge database now and we get our hands grubby and what have you, you end up thinking, oh, I wish I could measure something now. And I'm asking you with these cells and perhaps go beyond the cells, are there some things in terms of measurement that would be very useful in real time?
Sure, that's very blue sky. So I think that from just an understanding of the sort of fundamentals that are happening within the Jameson cell, I think a lot of these froth stability, froth recovery type devices would be interesting. I know that Lizette's PhD looking at scavenger Jameson cells. It's one of the areas that she wants to look at. And there are some physical constraints with putting some of these devices into a Jameson cell that has, froth trays in the way and these kinds of issues. So that's the one that kind of springs to mind in terms of research. Yeah, I think the froth phase is really probably the most important for us to understand.
Right. Well, if there are no further questions, please join me in thanking Chris for his presentation.